Sorry. Good afternoon, dear colleagues. I'm Zoya Eremenko. I'm from Ovsikov Institute for Radiophysics and Electronics, National Academy of Sciences of Ukraine in Kharkiv. But now I'm in Germany in Leipzig Institute for Solid State and Material Research in Dresden. My presentation is the excitation of the phase plasmon-polaritons in graphene by electromagnetic field using finite-element electromagnetic simulation. It's my short description or some short knowledge, maybe not new for you. What is graphene? Graphene is one atom thick layer of carbon atoms arranged in a hexagonal lattice nanostructure. Graphene goes from some other elements in nature, such as diamond or graphite. And these two elements has two different properties. For example, diamond has atom. Diamond's atom is bounded to 4 other atoms, and graphite atoms is bounded only to 3 atoms, other atoms, like shown on this picture. Graphene properties very unusual. If you can see on this slide some main properties of graphene. And as you know, I think the first explored the graphene properties was Valence in 1947. And in 2010, we have 2 Nobel Prize researchers, Andrei Geim and Konstantin Novoselov. And in 2014, inverter Larry Fillerto have a patent, a process for production single-layer graphene sheets. Phase plasmon-polariton in graphene. It's a wave, electromagnetic wave that travel along the metal dielectric or metal air interface, practically in the infrared or visible frequencies. And this plasmon-polaritons waves has some properties like shown in the screen. Optically, graphene has conductivity that the real and imaginary part of this conductivity shown on the picture. And in blue region, we have a real part of the conductivity much less than imaginary part. Only in this region, we can achieve or find plasmon-polariton propagation waves. And this is the Kubo formula for description these 2 lines in the graph. There is dispersion equations for TM mode and TE mode. We use TM mode in our calculation and modulation. Modulation was in console multiphysics software. On this screen, we have a screen with console project and some console features. Surface plasmon-polaritons we modulate in 2D simulation in graphene monolayers. As shown in this picture, we have port 1 and port 2, and there is these waves that goes along the thin graphite sheet. On this picture 2 and 3, we have dispersion lines for real part of wave number and for imaginary part of wave number. And on the picture 4, we have dependencies for propagation length and on the frequency. And there is there is some theoretical research for gain in graphene. The authors in this paper take two-layer graphene and make theoretical research. In yellow, the areas for potential surface plasmon-polaritons with gain, in this way, in this picture. This bilayered graphene was taken as A-B stacked graphene. And on this picture, there is frequency dependence of real and imaginary part of optical conductivity in this bilayered graphene. On this picture and on this also, I point the potential area where we can later, I'll show later, I found the gain in with surface plasmon-polariton waves. This is a dispersion equation for real and imaginary part. On this picture, there is propagation length in the narrow frequency range that have damping here. It's a picture of a propagation wave, no damping stage and gain stage. And on this picture, I can show you some videos that present when how from this part waves go to change their property. There is some conclusion for this part of presentation. As we obtain during the study of the 2D model for AB stacked bilayered graphene, and have a good agreement with the theoretical data. We found three regions with damping, with zero damping state, and with negative real part, and it leads to no existence in other frequency range gain. And this is another part of my presentation. I show the possibility of 3D model in console to simulate surface plasmon-polariton waves in 3D model. These waves can be excited by plane wave, and with using the tip sample junction in a SNOM microscope. In this picture, there is a design of such a model. And there is electric field distribution and definite frequency. This is the distance between tip and the substrate. And there is, I'll show as an example, the paper in which there is experimental observation of these waves as shown on this picture, and in these videos I can show you the console modeling results in this triangle sheet of graphene. It's shows that this modeling is very similar to the experimental one from this paper. And this is the rectangular sheet of graphene, and also we have the same, maybe very good, agreement with the experimental data. Thank you for your attention.
Thank you for your presentation. So do we have a question towards Professor Zoya Eremenko? Maybe, Andrzej, you have some comment or question? You deal with graphene.
Yes, but right now I don't have like any.
All right, so maybe I will have a question. So you are using COMSOL packet, right?
Yes.
Yes. So to what extent, because your treatment of electrodynamics is quite classical here, right? You treat
Yes.
electric field as classical object, right? Like
Yes.
So do you have any features of necessity that do you have any necessity to go into quantum electrodynamics more deeply? Can you grasp such way of modeling?
Now I present only modeling on the level of microscopic electrodynamics in COMSOL.
I see. But I believe the COMSOL is only representing electric field in classical way, right? So,
Yes.
do you have any plan for extra corrections that can account from quantum electrodynamics?
Yes, I think about it.
Any particular hints or suggestions or initial results in that direction?
No, not yet. I haven't now any results outside of classical electrodynamics in COMSOL.
All right. Okay. Anyway, it's quite inspiring for us, so we would be happy to think in that direction.
Thank you.
Right. Do we have any other questions from the audience? Maybe Zoom audience has some questions, please. So, and maybe I have another question towards you. Since before, you have developed your own code, right? I remember we met in Kharkiv like 1 year before this terrible war. So, do you have any chance of usage of your previous code in the context of given problems?
Your question about how I can apply my previous results in present work?
Yes, yes.
We already published a paper in IEEE theory and techniques, transaction microwave theory and techniques journal with our results. That previous results.
I see. All right. All right. So we are happy to. Is there any other question towards Professor Eremenko? Yeah. Yeah. So there is one of the audience. He will come. He was studying graphene in his PhD. Go ahead, Andrzej.
I have a question because I maybe missed it, but what was the substrate of your sample? You put graphene on some sample, yes? I mean, graphene samples on substrate. Did you mention the substrate you put it on or not?
Oh, sorry. Your question, yeah, your question about substrate?
Yes.
Because maybe I missed it somehow, but it's just out of my curiosity. What was the substrate you used for this sample?
Oh, sorry. I use substrate as a silicon oxide on this modeling, and on the modeling with gain, we on this slide I used the same substrate and substrate as an air.
Okay, thank you.
Because, excuse me, because it's not so great difference between air and other substrate with the electric. Only only maybe the wavelength of graphene of this waves surface plasmon-polaritons is changed. The maximum wavelength for this wave is when the substrate is air.
Okay, thank you for that. Thank you for answering my question.
Right. Maybe I have one more question. Do you know Professor Oleg Yermakov? Oleg Yermakov? Probably no.
No.
Because in his model, in certain situations you have TE and TM mode intermixed. Can you find such possibility in your system? Because usually TE and TM mode are separate, right? But is there any chance for combined occurrence of those modes, oscillating modes?
I understand your question. I study such a possibility for find the interaction between two modes in another modeling with some dielectric disk that placed over the graphene.
Yes. All right. Sounds good. All right. Do we have any more questions? If not, let us thank the speaker again. Thank you so much for your contribution and your talk.
Mhm.